Okay, welcome to this video that is to accompany Worksheet 1 for Math 221. So, I like to list the topics at the top. One piece of advice before we start, because this is our first lesson. This is probably being hosted on YouTube, and please experiment with playback speed. If I'm talking too fast, then slow me down. You can slow me down to 0.75 speed or speed me up. And I would recommend like 1.25. I would recommend one of those, either normal speed or plus or minus 25% are probably the most useful options for you. And so you will find the speed at which you get the most out of the presentation. Okay, now, first topic should be no surprise to anybody. It should be something you did early in your mathematical career. So a lot of things we're doing this week are very much review, but they're very important. So we have to make sure that we've covered them. And I'm going to give some commentary about this. So if you have 2 points and you want to make a line, let's say you have x naught, y naught, and x1, y1, okay? So that's generic, and of course when x naught equals x1, you have a vertical line instead of a horizontal line. Is not a function. Okay, we'll talk about that more, but it is a line, but that's not going to happen right now. We're not talking about non-functions primarily in this class, so that's not something we have to worry about too much. Okay, so what do? We're going to do, I want you to think of a line as anything where if you have any 2 points on the line, they have the same change ratio, because calculus is all about change and change ratio. And so I want you to think about the line is that place where if you take an arbitrary point and you say connect it by a little line segment to, let's say this is x naught, it's the same slope as if you connected x0 and x1 together. Okay, so that's the whole point of what it means to be a line. So it makes sense that we make this we say, all right, change between, so y1 minus y0 over x1 minus x0 is identically equal to, say, y minus y naught over x minus x naught for some arbitrary x and y pair on the line. So this x and y that's in red is this red point here. So any arbitrary point can be thrown in and say my comparison to x naught y naught is the same. So here's x naught y naught x1 y1, and this red point is just an arbitrary x y. That's what I want you to think. Now, if I've convinced you of that, then the next step is clearly we just solve this thing for y, and then it's a little more convenient if I flip that. Okay, so I just flip those around to make it a little easier, and then what am I going to do? First of all, you know that this whole mess here we like to call m. So I'm just going to replace this whole mess with the letter m, that means slope, and then I'm going to put this expression that's in the denominator, this just ends up right there, and then I'm going to say, oh wow, I'm just going to move this guy over to the other side. Ding! But when you move stuff to the other side, you got to change the sign, so I'm going to turn that into a plus, of course, and then I've got myself solved and we're ready to go. So you can just use this in your worksheet. You can use that form. You can solve for y equals mx plus b form if you like, but that kind of defeats the purpose of this particular exercise. I just want you to focus on the idea of slope and slope equality. So this is perfectly fine. This formula for the line, your worksheet question, your quiz question rather, is going to be matching, so you don't have to break it down farther than that. Okay. If m is positive, of course, the function is increasing, and the way you want to say, like, what do you mean by increasing? Because what I mean by increasing is if I'm driving from x being small to x being larger, this is the way we read in English, and this is the way we follow our axes in math. We go from left to right in most cases. So when I say increasing line, I mean as x goes from small to large, what's happening to y? They're going both in the same direction. Then m is positive, and we say our function or our line is increasing there. Okay, and if the slope is negative, the function is decreasing, and of course if the slope is 0, then that function is neither increasing nor decreasing. It is flat at that point. Okay, now talking about domain and range. If I have, I'm just showing the first quadrant here, but let's say I have a Cartesian axis here, and I have some kind of activity. I don't know, any kind of thing going on in here. And my function lives someplace in there. I want to think of my domain as being what happens if I take a sunshine up here and I get a shadow down here, then it tells me where the domain is. So from here to here, this guy is the domain. Okay, so you can also think domain means input. So input to a function or relation of some sort, usually a function. You have another word for independent variable. And another word, if you're a statistician, we call this the explanatory variable. Okay. And in graphing it, we usually put it on the horizontal. That's not necessary, but that's typical. And when all other things are equal, we usually call it x or t. So a lot of students will say, oh, the x variable, but what they really mean is the independent variable. And similarly, we have the situation over here where if we take a sunshine, I like to take the sunshine all the way over here and shine the light this way, then all the shadow on this side would be called the range. Okay, in the range we have the same situation as the domain. We have a whole bunch of words that mean the same thing. We can call them output. So if you're thinking of a computer, it's your output. It's your dependent variable. It's your response variable. And it's on the vertical, usually, not always. And it's anything usually other than x or t. It's usually this capital letters or y or r or anything like this, p. All those letters are typically used for the dependent variable. Again, this is just an arbitrary choice. You can use any letter for anything you want, and it's often the case that as soon as the instructor does that, you confuse the whole class. So I usually try to keep to these conventions, but don't expect that that will always be the case. In the various worksheets, you will see diagrams, and many of them are reused, and many of them are on a piece of graph paper that looks much like this. So I wanted to just make a comment about this. In this particular type of setting, I want you to assume that one of these boxes is 1 unit box that is 1 unit in the x direction and 1 unit in the y direction. So in this specific type of exercise that uses this kind of graph, you will not be given labels on the x or y axis because that assumption is being made. So for example, this is at 2, 3. So this empty circle here is at the location 2, 3, and the empty barbell means the point is not included. So for example, in this diagram, the function itself is that location is 2, -3 at that location. Okay, so that's just how to read these diagrams. I understand that these are kind of tiny, but you're able to zoom in on that and figure out exactly where that is. If you're close to an integer, assume that you're at an integer. So that would be at the location 3, 4, 5, -5, for example. I would assume that that's close enough. If it's something like this, it's close to a half. So I would say 1, 2, 3, 4. This is at -4, and I'm going to go up 1, 2, 3, 4, 5.5, so 5.5. So these are somewhat, they're not really computer drawn, they're half computer, half by hand, so they're not completely perfect. So you're going to go to the nearest integer if it makes sense, or nearest half if you're right between two items. I will try not to make things too ambiguous. Okay, on this diagram you have a couple neat things. You have an asymptote, so you go 1, 2, 3, 4, 5, 6. So you have an asymptote at x equals 6, for example. And you can see this point, just because of the drawing, what it means is it's reminding you as this curve approaches the point 4 of 6, 4, that point is not included. And then there's an asymptote from the other side. So again, within artistic considerations, try to interpret these diagrams. Also notice in this particular diagram there's a gap, so it's like this is -4 and this is -5. There are no points between -4 and -5, so there's a crazy discontinuity in that function. But what it means is this function is defined at 1, 2, at -4 this function is defined, but at -5 this function is not defined because this barbell is empty. This little circle is open, it's white, so it means there's no point there. Whereas this circle is black, it means there is a point there. Okay, so what does it mean to be a function? So the typical thing a mathematician does is they put the domain in a little oval like this and the range in a little oval like this, and then they say, here's all the various points in my domain, here's all the various points in my range. And there's some good to be done by this diagram, but there's some weaknesses too. But what they'll say is for every point in the domain, it maps to a specific point in the range. However, it's okay if I recycle some of the range values. So this might not be exactly 1-to-1, so you may have some overlap. In that case, we have to remove those other points from the range. They're not really in the range if they're not connected to anything in the domain. Okay? So you can reuse points in the range, but not in the domain. If you want to make sure that your function is invertible, you make everything match up exactly 1 point to 1 point. So for example, you would have to do something like this. This guy goes here, this guy goes here, this guy goes here. This computer is trying to be too smart on me. And that guy goes there. Okay, so if it's like a patch bay, you're literally connecting wires in a patch bay and everything goes from one domain to one range and you can't recycle anything, then it is a function. So think of this as a patch bay. If you don't know what a patch bay is, let me see if I can find one for you. Okay, this is basically a patch bay. You could have a big patch bay or a small patch bay, but things are going from one place to another. It could be in a recording situation or radio situation, but there's some kind of electronic signal going from one place to another. You can think of an old-fashioned telephone operator patching two calls together. Okay, here's an example of a telephone operator at a patch bay, and if you want to just Google that, you can see lots of pictures of that. But the idea is a call comes in and it's coming from one place, and the telephone operator literally patches with a cable, patches two callers together so that they can speak directly to each other. And in this situation, it's usually the cause for some kind of comedy show where the operator is listening into the call. And but that's I don't know how common that was, but it's very common in comedy that the operator is listening in. So anyway, that's what I mean by a patch bay. Okay, so an invertible function, if it's invertible, it has to be of a patch bay format. You go one way, you go the other. There's a one-to-one connection between the domain and the range. Okay, there's another way you can sort of test this. It's called the horizontal line test and the vertical line test, and that's the one you probably remember from your studies. If you have some function, it could be wiggly, 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 and you do something called vertical line test, where you take a vertical line, as one thing I can do more easily on the computer than I can do on the chalkboard. Okay, Thank you for small miracles. Anyway, this guy passes the vertical line test. Okay, so this guy is a function because as I'm drawing my vertical line through, I'm only touching at one point at a time. Okay, if however I have something like a circle, right? A circle does not pass the vertical line test, and then it is not a function. So what I do is I take myself a line and I say, oh my gosh, it passes through the circle at more than one point at a time. It passes through, say, here and here. All it takes is one contradiction to say something is not a function. But in order for it to actually be a function, it has to completely pass. And so you can't really draw a diagram to show that it passes the vertical line test. You just have to do it and say, well, that passed. Every input has exactly one output. Okay? Now, of course, if you want to know if a function is invertible, okay, then what you do is you not only have to pass the vertical line test, but the horizontal line test, because you want to see if it's going to be a function in the other direction. So you pass a vertical line through and you say, aha, it passes the vertical line and the horizontal line test. It must be a one-to-one patch-based situation. Okay, and then I can conclude that the function is indeed invertible. Okay, so this f of x notation is something that you probably know by now, but just in case you don't, it's important to clarify these. Okay, so f of x, if I say f of x is x squared, what I mean is f is the name of my function, and this is indicating what my input is, and this guy is my output. Okay, if you don't like this notation, I'm okay if you, as a hack, you're going to say y equals x squared, and it means exactly the same thing, but you didn't give it a special name. You're just giving it the name y, but you're not explicitly saying what the input variables are. Okay, so the f of x this function notation is much more explicit. It can be used for functions with multiple variables, so you could say, you know, g of x, y, z is equal to 3x plus y plus z squared. You could do something like that. So the function notation is great because you're calling out exactly what the inputs, how many inputs there are, and then if you need to use them, it's obvious, you know, they have to go in a certain order and so forth. And it's really good for computer programming. But that's what that means. So for example, if I have f of x, let me see, f of x equals x squared, and g of x equals 3x plus 1, then I can do something like f of 0 equals 0, f of 1 equals 1, f of 2 equals 4, f of 5 equals 25, and so on and so forth. G of x is equal to g of something, g of anything. G of 1 equals 4, g of 5 equals 16, and things like that. But what I get for free with this notation is now, because this guy is invertible, at least this is invertible if x is greater than or equal to 0, then this will be invertible. I can put that restriction on my function in order to make it pass both the vertical and horizontal line test. Then I can say something like this: f inverse of 25 equals 5, f inverse of 4 equals 2. So I have a built-in notation that indicates that I'm taking the inverse of another function, okay, and so on and so forth. So this allows us to have this built-in way of describing something. You can also nest these quite nicely. F of g of 3 is f of, well, what is g of 3? G of 3 is 10. And what is f of 10? F of 10 is 100. So that's the way those things nest together. And you can also nest the inverse functions together. So you can say f of f inverse of 72 is going to still be 72. And f inverse of f of 17 is 17. And I'll let you guys think about why that's the case. Speaking of inverse functions, how will we compute an inverse function? So graphically what you're doing is you're trying to flip x and y. So it's very common that we write a y equals x line, especially if we're going to do some kind of graphical inversion. Now this does not pass the vertical line test, but just for the sake of argument, I can still give you the inverse of this function graphically. All I have to do, and if I were in class, I would take a piece of paper and draw that red line on a piece of paper, then fold. You're going to fold on that line, and then you're going to transfer the ink so you get like a butterfly, like making like a butterfly curve. So whatever red does here, here's my F, then I'm going to make my F inverse look like that. Okay, and again, this isn't a function. When you invert it, it's not a function anymore. But graphically, there's no problem with this technique, even if the thing isn't actually invertible. But you should be aware of that symmetry. But how do you compute this? Compute this inverse. You just switch x and y, because usually you got an x and a y, and solve. So that's the usual technique for these kind of exercises. So here's an example. Y is equal to 2x over 4 plus x, and then you want to find the inverse function. Find inverse. So what you do is you say x is equal to 2y over 4 plus y. I'm going to multiply both sides by 4 plus y. So I'm going to get 4x plus xy equals 2y. Then I'm going to want to get the y's on the same side and solve for y. This is not the only way to find an inverse function, but it is what you're going to want to use for the exercises in worksheet 1. So this is the most straightforward way of doing this type of calculation. And then you've got yourself an inverse function. I don't want you to think of x and y's being specific things on the axis. It just is a space for an input and a space for an output. You might want to graph this thing. Whatever you do when you graph it, if you would just flip the x and y axis, literally like through a mirror, you put a mirror on the y equals x, put mirror at y equals x, and then you'll just see this. But want to graph this. Let's go ahead and graph this. You should become accustomed to using Wolfram Alpha in a responsible way. Okay, there's a responsible and an irresponsible way to use this tool, and we will probably continue to talk about that over the course of the semester. But for quick little plots, this is a really good thing to use it for. You can see different views on this. You can see there's an asymptote at x equals -4, and that's great. So what if we plot this guy and x, y equals x, see what that looks like together, and then we'll plot the inverse function together with that. Okay, so, and I want to plot minus 4x over x minus 2. There's definitely pluses and minuses with Wolfram Alpha. If you have a tablet that you like to work on a lot, I recommend go ahead and paying the extra couple bucks, I think it's $2 or $3, to download the Wolfram Alpha app, because it behaves differently from Wolfram Alpha Online. It has some features. Sometimes the online version is better and sometimes the app version is better. So it really depends on what it is you're trying to accomplish. But I've found that having both available is kind of nice. All right, let's see what happens if we restrict the domain a little bit to get a better picture. Maybe we can look at this better. I'm trying to get a good aspect ratio on this, and Wolfram Alpha does not seem to want to give me that. So you're not going to get this. This is actually 45 degrees, but it doesn't look like 45 degrees. So this blue line and this like yellow line, they're actually mirror images of each other, And I'm sorry it doesn't look like it. But it is. It really is. Trust me on that, or find a better graphing software. Let's try Desmos. Desmos is sometimes good for this kind of thing. I think between Desmos and Wolfram Alpha, those are pretty much the top two graphic tools you might want to use in this class. So I'm going to just plot x, that's easy. And I want to plot minus 4x over x minus 2. And I want to plot the other one, the original function I had, which is 2x over 4 plus x. And there we go. And in Desmos you can see this beautiful graph. They pride themselves on being beautiful, and in this time they win. They totally win that one. They made a beautiful graph for us, so that's great. I could put that on my wall. That's pretty. Okay. Let me think about this. Now it's probably the right time to tell you what the workflow is in this class. So first, you're going to watch the video. You're watching video for Worksheet 1 now. Take notes on anything that's new to you. Lots of stuff you won't need to take notes on, but if it's new, make sure you write it down. You will possibly want to glance at the worksheet prior to class. That's not required, but it's encouraged. I would spend 2 or 3 minutes just glancing and saying, yep, those questions are what was just covered in the video. I'm ready to go. Then you come to class ready to work on the problems in small groups. When I open up class, I'll only spend a couple minutes taking attendance and saying good morning to everybody and making sure everybody's ready to go off into their groups. At that point, if there's some major question that has come up in office hours repeatedly, I might address it there, for example. But within a few minutes, you're going to be broken out into your small groups. During that class time, you're going to converse with your small groups about the answers to the worksheets, and you're going to work on those problems. Roughly halfway through class, you're going to start keying in some of those answers into the quizzes. Everybody has the same quiz. A quiz is quiz in quotes. You can take it as many times as you want. You can converse with each other. It is not cheating to talk to each other about the questions and the answers for the quizzes. The quizzes are just in quotes. Okay? It means it's actually a check on your worksheet to make sure you're getting through the worksheet correctly. Then make sure as you're working through the worksheet with your classmates that you get to the hardest problems first. If you see some are easy, just skip those and do those on your own later. Work on the hardest questions in the group. Make sure that by the time you finish your group work, you're ready to finish the worksheet on your own. Your quizzes have infinite retakes, so for example, it's totally fine as you're working through to say, hey, I wonder if we're doing question 4 correctly. Go over to the quiz, have one of your classmates key it in and say, yep, we're good, we understand question 4. Let's go to question 5. That's a good workflow. Okay, and if there's any questions after you break out and you're working on this later, you say, oh gee, I think I'm going to drop into office hours and ask a question because I was working on the worksheet and I got jammed up somewhere. That's your workflow. It is okay to ask questions out of sequence in class, but it is preferred to stay on topic. It is preferred that we work on whatever the day's worksheet is. But every so often, other questions will percolate up, and that's okay. That's fine. You're on worksheet 5, but you were just working on worksheet 3 yesterday, and you have a quick question on that. That's fine. I'm going to circulate through the different tables while you are working, and I will also leave a doppelganger of myself in the main room. So there will be a main room, our main classroom, and if you need to get my attention, one of your classmates can leave the table and come to the main room to come find me and say, hey, when you get a chance, we have a really big question. We're stuck. Can you please come back to our table? And then that's how you'll get my attention. Okay, hope that all makes sense, and I look forward to meeting you really soon.